Welcome to Geometry Lesson 6.3. We are proving parallelograms. In Lesson 6.3, we'll learn what makes a quadrilateral a parallelogram. We have 6 more theorems. Many of these theorems will look familiar, and that's because 6.3.1, 6.3.3, and 6.3.4 are converses of theorems from Lesson 6.2. So the drawings that go along with them will look very familiar. Theorem 6.3.1. A quadrilateral is a parallelogram if both pairs of opposite sides are congruent. In this figure, we have quadrilateral A, B, C, and D. Line BD has been drawn so that triangle ABD and triangle CDB are congruent by side, side, and remember that when you have parallelograms divided by diagonals, you create a side that is shared by both triangles. So this will be the third side, BD. To express that, we say that BD is congruent to DB. That's reflexive property. And therefore, we can now state that angle 1 is congruent to angle 2. And that is because of alternate interior angles. If we have alternate interior angles, we are now implying that AB, side AB, is parallel to side DC. We can also state that angle 3 is congruent to angle 4. This implies that BC is parallel to AD, also by alternate interior angles. Therefore, we've proved that quadrilateral ABCD is a parallelogram. We've learned that any quadrilateral with 2 pairs of parallel sides is a parallelogram. There are also other methods to prove that quads are parallelograms. So we have 2 sides of this drawing, this quadrilateral, that are parallel. Theorem 6.3.2. A quadrilateral is a parallelogram if one pair of opposite sides are parallel and congruent. In the figure, line AC has been drawn so that triangle DAC is congruent to triangle BCA, and this is by side, angle, side. So they show that it's DAC. They're using DC, angle 4, and the shared side of AC to prove that both triangles are congruent. In this triangle, they're using side AB, the angle number 1, and the shared side. AC is congruent to CA by reflexive property. Angle 1 is congruent to angle 4. That implies, because of alternate interior angles, that AB is parallel to DC. Once this is stated that the 2 triangles are congruent, we can now state that angle 2 is congruent to angle 3 by CPC-TC. Now we can finally state that quadrilateral ABCD is a parallelogram. Theorem 6.3.3. A quad is a parallelogram if both pairs of opposite angles are congruent. In the figure, we have angle A congruent to angle C, angle B congruent to angle D. Because the angles are congruent, their measures are equal. If we were to add all four of these angles, they would equal 360 degrees. That comes from theorem 6.1.1. We now know from other theorems that we've learned in this lesson, in this chapter, that angle A plus angle B are supplementary. Angle C plus angle D are supplementary. That both pairs of those angles individually equal 180 degrees, and that's the definition of a quadrilateral. Therefore, we can say that AD is parallel to CB, and this is because, and we can also state that AB is parallel to, let me try that again. AD is parallel to CB. AB is parallel to CD, and that's because of supplementary consecutive interior angles, and they imply parallel lines. That is also from a theorem from this chapter, and we can now state that this is a parallelogram. My recommendation when you're doing the work in this lesson is that you have your list of theorems next to you with your pictures, and that you'll be able to pick out which theorems you can use to prove these figures. You'll find that there may be more than one way. Theorem 6.3.4. A quad is a parallelogram if its diagonals bisect each other. So in this figure, we have quadrilateral ABCD. BD and AC, which are diagonals, bisect each other. X is their midpoint. This creates a situation where AX is congruent to CX, and let me change colors. And BX is congruent to DX. We can also state that angle AXB, this angle right here, is congruent to CXD. And we can state that BXC is congruent to DXA. That is because of vertical angles. Therefore, these two triangles, AXB and CXD, are congruent to each other, and the other two angles, BXC and DXA, are congruent to each other by side, vertical angle, side, side angle, side. Now we can talk about their angles, and we have BAX is congruent to DCX, DCX right here. And we can also state that BXC, let's see, CBX, CBX is congruent to ADX by CPC, TC. Now we have all of these segments congruent. We proved two triangles are congruent by side angle side. We can now state that line AB is parallel to line CD. Line BC is parallel to line DA by alternate interior angles. And now we know that we have a parallelogram, ABCD. So this is very similar to opposite angles are congruent to each other. We've only proved one of the angles in these triangles, but that would mean that the other angles would have to be congruent by CPC, TC. Let's take a look at an example. Determine whether each quad can be shown to be a parallelogram. and then explain why. So let's take a look at A. A is a quad, DEFG. We have two measured angles right here, and we have two congruent sides. This is a parallelogram by theorem 6.3.2. Let's go back and look what 6.3.2 was, and that's where if one pair of opposite angles are parallel and congruent, then and sides, one set of sides are congruent, then you have a quad, and that's exactly what we have. So, angle G and angle F are supplementary. They add to 180 degrees. DG is congruent to EF, and therefore DG is parallel to EF. Let's take a look at B. Well, it looks like a rectangle, but it's not marked properly to be a rectangle. In fact, if you were to draw sides that match these angles the way that they're congruent, you'd probably end up with an isosceles trapezoid. So no, the opposite angles are not congruent. You can see that. Consecutive angles are congruent, but the opposite are not. And let's look at C. C, once again, looks like a rectangle. It has two 90-degree angles that are congruent, and one pair of consecutive supplementary angles doesn't show enough information to say that these are parallel. We would have to have one set of sides, just like we have in A, that are congruent. Example 2A. Find the value of each variable that ensures that each quad is a parallelogram. So let's take a look at A. What do we have here? Well, we have a quadrilateral PQRS, and it has two diagonals that bisect each other. That means that you're going to have congruent, and let me see if I can find my cursor here. You'll have congruent segments. So in this drawing, you have ST congruent to QT, and you have PT congruent to RT. So let's begin with this segment right here, QT and ST, and we state them equal to each other. So we have 5A equals 20, which would simplified be A equals 4. Let's look at the other set of lines, and we have 7B minus 4 equals 6B plus 2. If we simplify, we find that B equals 6. If you happen to put your information the other way around, 6B plus 2 equals 7B minus 4, that's fine. You'll just end up with your B over on the right. Now we have two values, so we have a value for A, we have a value for B. And we can substitute into our equations. So 5 times 4 equals 20, and QT equals TS, and they are both 20. 6 times 6 equals 36 plus 2 equals 38. So PT is 38, so that means that TR should also be 38. But let's take a look. Let's work it out anyway. 7 times 6 equals 42 minus 4 equals 38, and that is correct. So you remember that the diagonals bisect each other, and they create equal segments in your parallelogram. You solve the system of equations that results using substitution, and you substitute the values in to show that the opposite sides are congruent. Let's look at 2B, and we'll be working similar equations, but we'll be using opposite sides. So we have values for all four sides of this quadrilateral. Let's begin with AB and CD. So AB is x plus 11, which equals y. So here's the x plus 11, and here's the y. X plus 11, we can't solve anymore. We have no other values to solve, so this is where we have to stop. On this opposite side, we have 2x and y plus 14, so 2x equals y plus 14. And we can sort or simplify to get a value for y here. And now we set these two equations to equal each other. X plus 11 equals 2x minus 14. And you say, well, why do we set them to equal each other? This is a parallelogram if both pairs of opposite sides are congruent. So that's what we're trying to prove. So x plus 11 equals 2x minus 14. And we have a value of x equals 25. And if we substitute the 25 into the y equation, 2 times 25 is 50. Minus 14 is 36. So x is 25, y is 36. And now we can substitute into our original equations. So x plus 11 equals y. 25 plus 11 equals 36 equals y, which is also CD. And AD equals 36 from our y value. 36 plus 14 equals 50 equals 2 times 25 equals BC. So they are equal to each other, and we now have our proof, and this can now be stated for sure that it's a parallelogram. We've already learned that dividing two polygons into congruent corresponding triangles allows the polygon's corresponding parts to be proved congruent. We do this by using CPC-TC, or by proving triangles with side angle side, 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 and so forth. The polygons must then, by definition, be congruent. This leads us to the next theorem, the polygon triangulation theorem, theorem 6.3.5. Two polygons are congruent if they can be divided into congruent corresponding triangles. So we've already done this. We've already taken polygons, divided them, but we were dividing quadrilaterals. We already knew they were quadrilaterals. Sometimes you'll have other figures, and you need to find out if the triangles created are corresponding. This theorem is applied in our next example. So with example 4, we have two sets of quadrilaterals here. We have ABCD and we have PQRS. They share congruent angles. They share congruent sides. They have been divided in half by diagonals. We're going to prove that they are congruent to each other. So we have our given, and I've already told you all the things that are in the given. We're now allowed to draw BD and QS using the line postulate. And we've created these triangles. We have triangle ABD, and it's congruent to triangle PQS, and that's by side, angle, side. We can now state that BD is congruent to QS. So these sides here, these diagonals, that's supposed to be 3 lines. Hopefully you can see that. Are congruent, and we're able to do that by CPC-TC. And now we can state all of our segments of our quadrilaterals. So AB is congruent to DC. And PQ is congruent to SR. AD is congruent to BC, and let me change colors. So AD is congruent to BC. And PS is congruent to QR. And that's because opposite sides of parallelograms are congruent. DC is congruent to SR. Now we're going from one parallelogram to the other parallelogram. And BC is congruent to QR. So BC and QR. And that's transitive property of congruent segments. It required us to use step 5 and step 1, part of the given. And we can now declare that BCD, the other triangle, and QRS are congruent by side, side, side. So we started off with congruent triangles ABD and PQS. Now we can state the congruency of the other two triangles. And therefore, parallelogram ABCD is congruent to parallelogram PQRS by the last theorem we just learned, the polygon triangulation theorem. This leads us to our last theorem in this lesson. This is theorem 6.3.6. And this is the SAS, side angle side congruence for parallelograms. If two consecutive sides and an included angle of one parallelogram are congruent to two consecutive sides and an included angle of another parallelogram, then the two parallelograms are congruent. So AB and AD are consecutive sides. PQ and PS are also consecutive sides. Theorem 6.3.6, side angle side congruence for parallelograms. If two consecutive sides and an included angle of one parallelogram are congruent to two consecutive sides and an included angle of another, then the two parallelograms are congruent. So we have quadrilaterals ABCD and PQRS. Because they share side AB with QP and side AD with PS, and they share congruent angles A and P, we can now state that they are congruent to each other. Your homework for lesson 6.3 is number 1 through 14. Numbers 44 through 49. Suggestions for number 2 through 6. Look at the theorems from this lesson to answer these questions. There will be two answers. Yes or no will be your first answer, and an explanation goes with the answer if you have answered yes. So you have to state why it can be a parallelogram. And don't just write the theorem number, write out what the theorem says. So say side angle side parallelogram or something like that. Just don't write the theorem number. That won't help you to retain in your memory why it works. Number 11 through 14. The drawings for these problems will show that the figures can have the named characteristics but will not be parallelograms. So you're going to draw contrapositive examples. They're asking you to make drawings that are not what they're asking for. So basically you're to make a drawing that disproves what they're asking for, if that makes sense. So if you have any problems with that, go ahead and contact me. Once again, my suggestion is to have your theorems written out when you start these videos, and to add the pictures as we go along. And this is basically the end of our first 3 lessons in this chapter. This is the bulk of the information that you're going to learn, so be sure that you know it well. Have a blessed day. See you soon.